Hi guys, I am back again with a tutorial video and it will be all about problem solving involving properties of solutions and thermochemistry. So I will be teaching you how to solve molarity, boiling point elevation, and the first law of thermodynamics, which includes the calculation of work, heat, and internal energy. So what is molarity? Molarity, it is the amount of substance in a certain solution. It is the concentration of a solution expressed as the number of moles of solute per liter of solution. Now let me give you an example. What is the molarity of a solution prepared by dissolving 15 grams of sodium hydroxide in enough water to make a total of 0.225 liters of solution? So in this problem, 15 grams is the mass of solute while 0.225 liters is the volume of the solution. To get the molarity of the solution, we first need to convert the mass to mole. So to get the mole, we also need to get the molar mass of the substance. So the molar mass is just the sum of the atomic mass of each component. The molar mass of sodium hydroxide is 40 grams. Now we use this in the formula of mass to mole, which is 15.0 grams of sodium hydroxide divided by the molar mass, which is the 40 grams, and then we multiply it to 1 mole, which is equal to 0.375 mole of sodium hydroxide. Now that we have the mole and the volume, we can now calculate the molarity of the solution. This is equals to 0.375 moles of sodium hydroxide divided by 0.225 liters. The molarity of the solution is now 1.67 mole per liter or 1.67 m. Now let's go to boiling point elevation. Boiling point elevation occurs when the boiling point of a solution becomes higher than the boiling point of a pure solvent. This happens whenever a non-volatile solute is added to a pure solvent. So to get the boiling point elevation of a substance, we need to multiply the Van Hoff factor or the I to the ebullioscopic constant and then to the molality of the solution. In this example, what is the boiling point elevation when 0.67 moles of ammonia is dissolved in 200 grams of water? The ebullioscopic constant for water is 0.52 degrees Celsius per m and the boiling point is 100 degrees Celsius. So to solve for molality, since molality is not given in the problem and molality is needed to solve the boiling point elevation, we use the formula, the moles of solute over the kilograms of solution. So this is equal to 0.67 moles divided by 0.2 kilograms, which is equal to 3.35 m. Now, since we have the molality, we solve for the boiling point elevation. Boiling point elevation is equal to I, which is the Van Hoff factor, multiplied by the ebullioscopic constant and the molality. So 1, the Van Hoff factor is 1 because for most non-electrolytes dissolved in water, the Van Hoff factor is essentially 1. So multiply to 0.52 degrees Celsius per m, which is the ebullioscopic constant, and 3.35 m, which is the molality. The boiling point elevation is equal to 1.74 degrees Celsius. If you want to get the final boiling point of the solution, we use this formula Tf, or the final temperature minus the initial temperature. Since it's the final boiling point we are finding, We'll be adding the final boiling point elevation and the initial temperature. So this is equal to 1.74 degrees Celsius plus 100 degrees Celsius, which is the initial boiling point of the water before the solute was added to the solution. So the final temperature would be 101.74 degrees Celsius. Lastly, the first law of thermodynamics states that heat is a form of energy and thermodynamic processes are therefore subject to the principle of conservation of energy. Now, in this part, I will be teaching you how to calculate the internal energy, heat, and work. This is the formula used to find the change in internal energy. U, or the change in internal energy, is equal to Q, or the heat, plus work. On the other hand, to find work, we need to multiply the external pressure and the change in volume. Before I give you an example, this is the sign conventions for work and heat we need to consider. When the work is done by the system on the surroundings, the sign is negative. When the work is done on the system by the surroundings, the sign will be positive. When the heat is absorbed by the system from the surroundings, or what we call the endothermic process, the sign is positive. And when the heat is absorbed by the surroundings from the system, or the exothermic process, the sign will be in negative. Now, in this problem, a gas does 125 joules of work while expanding, and at the same time, it absorbs 150 joules of heat. What is the change in internal energy? So the given in this problem are 125 joules of work and 150 joules of heat. But as I have said a while ago, when the work is done by the system, the sign will be in negative. So the work here would be negative 125 joules. On the other hand, the heat remains positive because it is the system that absorbed the heat. So it would remain 150 joules. Now let us solve this problem using the formula for change in internal energy. Change in internal energy is equal to Q plus W, which is heat plus work. 150 joules plus negative 125 joules, which is just technically 150 joules minus 125 joules. So the change in internal energy is 25 joules. The last problem, calculate the heat and work of a gas that expanded from 40 ml to 95 ml at a constant pressure of 3 atm. The change in internal energy is 20 joules. So the given in this problem are the initial volume, which is 40 ml, the final volume, which is 95 ml, pressure, which is 3 atm, and the change in internal energy, which is 20 joules. Now, first, we need to convert the milliliters to liters. So, the initial volume, which is 40 ml divided by 1000 ml equals to 0.04 liters. Now, the final volume, which is 95 ml, we convert it to liters. It would be 0.095 liters. Next, we need to find the change in volume, which is final volume minus initial volume. So this is equal to 0.095 liters minus 0.04 liters, which is equal to 0.055 liters. Now that we have the volume and the pressure, we can now get the work, which is negative pressure multiplied to the change in volume. This is equal to negative 30 atm times 0.055 liters. Work is equal to negative 165 liters per atm. To convert the liter per atm to joules, we multiply negative 165 liters per ATM to 101.3 joules over 1 liter per ATM, which is equal to 167.15 joules. Using the formula for change in internal energy, let us find the heat. Q is equals to change in internal energy minus work, which is equal to 20 joules minus 167.15 joules. The heat in this problem is equal to negative 147.15 joules. That is all in this video, and I hope you learned something. Don't forget to like, subscribe, and hit the notification bell for more updates. Thank you and stay safe.